So it's a pleasure to introduce you or to present here to have here actually Chiara, Poletto. There is a small introduction. I didn't tell you about that, but she did a PhD with Maritime, no? So in Padova. Mistaken. And then after that, she came to ISI, to Torino, to work as a postdoc. So we shared the office for quite a while. And now she's in a kind of changing situation, no? So because she's moving to Paris, to Inserm, which is the Institute of Health of the French government. You are essentially catching postdoc from our base to in Paris. But he still remains as officially interim. She's in Paris now, so I won't change it somehow. So well, she has been working the last years, especially after the PhD in epidemiology. And actually we have worked in several of the works that we have about the flu and so. But now they are moving also to other pathogens. So I think this is what the talk will be about. So it's the process of business.
Okay. So thank you very much to Cosette for inviting me here. So I'll talk about the role of human mobility in the spatial preparation of epidemics. In particular, several complex and heterogeneous aspects characterize human mobility behavior on one hand and pathogens on the other. And I want to study the impact of this aspect on the ability of an epidemic to reach pandemic proportions. Okay, so human mobility is a fundamental vehicle for the geographical propagation of epidemics. The spread of epidemics carries the signature of the human mobility pattern. And here I'm showing you a picture of the recent H1N1 pandemic. This is the spreading pattern at the early stage from real data. And we can see that the epidemic was able to spread very fast in a few months in each of all the countries. And this is due to the extremely efficient transportation media available nowadays. But also we can see this spreading pattern that may appear random at the first glance, but actually it followed the roots of the air transportation network. So human mobility has to be an ingredient of epidemic models, but actually, it's quite a complex process. So we can represent human mobility as a network in which we have locations that are nodes, for instance cities, and then we have fluxes of traveling people that are weighted links of this network. But this network is multi-scale and it displays heterogeneous feature. For instance, here I'm showing you the analysis of the worldwide transportation network. So we can see that, for instance, that the degree distribution is power-like, with most of the nodes having a few connections, but there are also hubs with hundreds of connections. And also the weights, so the number of people traveling along each connection is a broadly distributed quantity that spans several orders of magnitude. And besides this heterogeneous aspect, we have also no trivial relationship that were pointed out among the quantities in the system. In particular, here I'm showing you a power law relation between the flux, the number of people traveling, so the flux, and along the connection, and the product of the degree of the two nodes, the two connected nodes. So beside this aspect related to the structure of the network, we also have further degree of complexity that are related to other levels, so to the individual level and to the pathogen level. In particular, at the level of individual, we see that the traveling behavior of each individual is characterized by complex feature, and I want to focus on a particular aspect that is the length of stay, that is the time spent at the destination. So this is an important quantity from an epidemiological point of view because it affects the probability of mixing among individuals and also the probability of interaction and transmission of the disease. But actually from statistics, it's shown to be very distributed, so it's not so easy to plug this ingredient in epidemic models. And another aspect is related to pathogen, that is genetic diversity. So for many pathogens, we have the coexistence of different strains, and this may affect in a non-trivial way the geographical propagation of epidemics. So during this talk, I will discuss about these two aspects separately, but for both of them, I have the same goal and the same approach. So the goal is to understand the impact of this heterogeneous feature on the invasion potential and epidemic, so the ability of a disease to reach the whole system and spread globally, and also to its spreading pattern. And I will use tools typical of network theory. So we have a theoretical approach to model the system and address these two aspects. So let's introduce the theoretical framework in general. So we use the metapopulation approach. That means that the whole system is divided in patches, in population. Within each patch, individual interact mix, and so the infection can be transmitted. And then we have the traveling coupling among patches, that is the mobility network. An individual can travel on this network, and so the traveling infectious individual can seed the infection in new locations. And so the epidemic spread is represented as a reaction-diffusion process. So here we are dividing the system in a local scale, that is the scale of the patch, and a global scale, that is the scale of the whole system. And basically to define a model within this framework, we need to define these three ingredients. That is the network topology and the traveling flux distribution, the first one. The second is the mobility model. And the third one is the transmission model within each patch. So, okay, let's start now from the first aspect I want to discuss. So, heterogeneous mental state. I will start from some empirical evidences on the problem. So we can see that from some statistic of UK that the length of stay is a broad distributed quantity. So most of the trips last few days, but there are also trips that last months. And also we can see that it's a geographically dependent quantity. So here I'm showing the map of UK, and for each city I'm showing the average length of stay in that city taken as destination of the trip, and you can see this geographical structure. Actually, we don't have a good data on that, so we cannot just take empirical data and plug them into the model, and we are forced to make some assumption. In particular, we assume that the length of stay is characteristic of the geographical location.
This is asking to the people that arrive there at the airport, or how this is estimated?
These data are statistics related there.
Hotel occupation, on the hotel occupancy, or asking to the people at the airport when they leave, how many days have you been here? How is obtained this data?
This is, I think, I should check, but I think that this statistic are in the airport. But if you want, I can. The problem is that we don't have, a comprehensive data set, a good statistic. It's difficult to find it.
Until that I miss the news. So UK is no longer part of the European
Union. Well, UK is
no longer part of the European Union.
Don't discuss with me about this.
That's the UK perspective.
No, I remember that. I got in this, but there was UK with Europe, UK with the US, and UK with the rest of the world. So this is the geographical map.
But but they use the rest of for the world, but not for Europe. So they do not claim to be out of the world, but they do claim to be out of the world.
So they should pay back all the money from the European Commission.
No, it's not a European Union, it's Europe.
Europe.
Okay, that was a joke, I'm sorry.
So they are part of Asia or
Do you have traffic which lasts less than a day?
Yeah.
They are not included.
They are not there.
could be.
Less than a day. I think 1 day or less. This is what was
Because they will go city for a few hours and come back.
But no,
But why to Madrid?
From Paris, you can have a day trip. Okay, so
Even from Dublin.
Which I guess is part of Europe.
basically, so now in order to define our model, we can define the 3 ingredients of our model. And so we start from the first ingredient, that is network topology, traveling fluxes. So I show you the statistics. So from this statistic, we can decide to define a synthetic network that keep the same statistical properties. So we set a power law degree distribution, and then we set the relation among flux of people and degree, the power law relation. And then I didn't show you the plot, but also a power law relation between the population of the urban area around the airport and the number of connections of the airport was pointed out. And so we can set this relation in our model. And so the central role of degree, as pointed out by this statistical analysis, justify an approximate way to handle the system, that is the so-called degree block approximation. So basically, all nodes with the same degree are considered statistical equivalent. So all the quantities characteristic of the node are considered as a function of the degree. This is a sort of mean-field approximation, but a refined way to introduce mean-field approximation in which we insert in some sense homogenize the system, but keeping the heterogeneity in the topology. Okay, so the second ingredient is the mobility model. So since we want to account for the length of stay, we need a model that keep track of the origin, location, and individual. So a non-Markovian mobility model. So here, individual travel to a given destination and after a while come back. A model like this was introduced in the past in the literature. So we took this model. Basically, it consists of dividing patches in subclasses according to origin of the travel. So we have, for instance, the class N prime K of individuals that are resident in the patch with the degree K prime, but in that moment representing the patch with degree K. And then we have the patch NKK, that is people resident there, represent there in that moment. So we have fluxes among these classes, so people living with a rate sigma K prime K, and people coming back with a certain return rate that is the inverse of the length of stay. So now we need to introduce the length of stay, and basically we make some assumptions. So we assume that in order to work within the degree block approximation, we assume that the length of stay is a power law function of the degree, and we do this because we introduce in this way this exponent key that tunes the level of heterogeneity of the length of stay. So we compare scenarios in which the average length of stay of the whole system is the same, but just the heterogeneity is different. And moreover, we can consider 2 different regimes. So when key is positive, we have a positive correlation between length of stay and degree. So basically, I spend more time where connected cities. When the key is negative, and in the opposite regime. So there is an anti-correlation between Ventus A and DV. Okay, so the third ingredient is the transmission model, and we want to keep it as simple as possible.
So one question. So people from a city of a given degree, they live at a given rate. So the statistics of these people would be exponential. But because you have many of them, in total you have a power law of whatever distribution of time. I mean, a person with a given that comes from a city with a given degree will live and come back at a given rate, constant in time.
Yeah.
So these people will have exponentially distributed times.
Yeah.
But because there are many people with different degrees, with different degrees, disaggregated.
Yeah, sure. It's exactly. Yes.
But the length of stay is not the characteristic of the origin place, but of the destination.
Yeah, we made this assumption.
So people who come from a place with a given K, you will have heterogeneity also inside this place, because people will go to different places and will stay different times.
Yeah, of course we could extend this model also to the case in which the length of stay is function both of the region and the destination. It could be interesting, but it's more difficult to make calculation in this case. Okay, so transmission model. Yes, this is the simplest way to model transmission within patches. So we assume that all individual mix homogeneously within the patch. We use the SIR model, that is the standard way to model epidemics. And basically we divide the individual in susceptible, infected, and recovered. So a susceptible can get the disease from its infectious one, and after a while it recovers. So this dynamics is ruled by a fundamental parameter that is R0, the basic reproductive number, that determine the transmission potential of the epidemic. And in particular, the basic reproductive number represents the average number of individuals that an infectious individual can infect before recovering in a fully susceptible population. So, if this is greater than 1, the number of infections will grow exponentially at the beginning, so we will have an outbreak. Otherwise, if it's smaller than 1, the first few cases will generate just 2 cases, and then the epidemic will die. So we have this condition for the epidemic. Okay, so now that we have defined all our ingredients, we can describe the invasion of the epidemics on the world system. So we will describe the invasion dynamics at the level of patches, and we will use the breaking process approximation. So basically, we divide cities, patches, cities in generation. We introduce this quantity that is the number of diseased patches at generation n. So at generation 0, we have just one patch that is the origin of the epidemic. And before the end of the outbreak within that patch, it will be able to infect a certain number of its neighboring patches. And this represents generation 1, and so on and so forth. So we can write down an equation that relates the number of disease patches at generation n to the number of disease patches at generation n-1. And we can do that in the degree block approximation. So we have number of disease patch within the degree block, the degree class K. So this is basically the equation that describes the invasion. And well, we have these 3 terms. The first one is related to the connectivity of the system, to the topology. The second term is basically the probability that the new patch is not yet infected. And the third term is the probability that the outbreak will take place in these new patches. So we have a patch of degree K prime that sends during the duration of the outbreak a certain number of individual, infectious individual to the patch with degree k. This number is lambda, k prime k. And so we have the probability of extinction of the epidemic generated by this individual, and 1 minus the probability of extinction is the probability of having an outbreak. So this term depends on the ingredient of our model, like mobility model and transmission model we are using. So for the case of a simple SIR, the probability of extinction has that simple expression. And but the number of individual depends on the mobility model, so it's specific for the non-Markovian mobility dynamic that I introduced before. And okay, so since we found explicit forms for all this quantity, basically we can obtain an explicit form for that equation and describe the invasion.
So you're neglecting looks, the networks.
Looks, yes. Yes, because it's a branching process of solution.
Probably it's smaller. So you're assuming that every treat is every traveler returns in the same path he did. Is this the approximation?
No, basically we assume that the network is a sort of tree-like, so it's very sparse.
But the communication network is not like this. Probably the traveling network on top
the
of
traveling
this.
network is, of course it's an approximation, but it's not so.
The traveling doesn't matter, so because in this model you assume that in the traveling there is no infection. This is when they are population, so they can only infect.
So connection to the employer.
Well, the connections play a role in the sense of from where to where it can go, but not in the sense that during the flight someone is going to get infected. So people can only infect when they are in the.
So when you go connection, you count that you first travel to the port and then, and from there you travel to the airport, not as two travels.
So it tells you how it can provide to different populations.
So what the mirror says that this time you do not allow to return in a different way the way you travel. I mean, the way and the
but
you have to travel and come back in the same way.
This is forced by this mobility
because
model.
it's a direct connection, so in theory you go from one to another and you go back. But you never do three jumps or things like that.
Yeah, this mobility model is quite strict in this sense. So people go in certain place and then come back. Actually, it's not so far from reality. Most of the trips are like this. So, yeah. Okay, so yes, we are here. So basically, if okay, so this is the equation that describes the invasion, and by analyzing this, we understand that it characterizes the invasion dynamics characterized by two different regimes. So regimes in which the epidemic is able to invade all the systems, so patches are rapidly infected. Now, another regime is a regime in which the epidemic is confined, so it gets extinct rapidly. So we can define a parameter that is R star, that is the invasion threshold parameter, that discriminate among these two regimes, and actually it results to be the analogous of the basic reflecting numbers. So if R star is less than 1, basically the epidemic is confined in a small part of the system. Otherwise, if it's greater than 1, we have an epidemic invasion.
I understand the level side, but the spatial part is missing. I don't get it. I mean, because you have a space, right? So you have neighboring patches. Probably the travel connection is too small because they are too close, and most people will travel by car or train. And this is not there, right? Or it is?
Well, actually, what you are saying is that what really matters is the structure of the network, and it's not the geographical distance. So what I'm saying is that New York can be closer to Paris than, I don't know, Marseille, because I'm kidding. But I mean, because if there is a fast, good connection between New York and Paris, they are very close.
Yeah, but New York is closer to New Jersey than Paris. Because there are a lot of people and the movement.
Yeah, but that can be.
But there is no plane between these two places.
There is no?
There is no plane connection, there is no air connection between them.
Yeah. Okay, what I'm introducing here is general framework. I mean, if you have...
Well, but for the spreading, I think the spatial part should be important. I mean, that's...
But you can account it in this network framework. I mean, if you have the whole network of that include both the traveling connection and both the commuting pattern, for instance, among neighboring region.
Or travel by car. I mean, I suppose
Yeah.
travel by car is not necessarily, I mean, you are assuming that has the same properties as the travel by plane?
Yeah.
This is an assumption for that? Or?
No. So this
No,
is
yeah,
just
yeah.
a theoretical framework.
Yeah.
So it's a theoretical framework motivated by how people travel by plane?
No. How
Yes.
people travel.
By
So
plane.
you don't say...
Yeah,
Is
so-
the distribution of people between two places depending on the number of connections by plane between these two places. So it's their motivation.
No, because the other thing that you assume is that there is a connection between the fluxes and the connection, the number of connections. But no one says that this is not true, for instance, for commuting, or is not true for...
Actually, okay, I was quite fast, of course, simplified, but the heterogeneties are found also for commuting network, for other kind of mobility network. So this is not for specific for flight. I mean, this plot is made for a transportation network, but I can show you an analogous for commuting, for instance.
Yeah, and K in commuting is what?
Okay, so there
K
are of connections.
But the problem is the mobility time scale, for instance. Well, this part is common, but for instance, this is not common because if I think on commuting, the time spent at the destination is few hours. I don't spend the destination months. So, okay, this is a theoretical model, more motivated by I transport. I had it in my mind, but it's quite general. Okay, so basically what we have here is that from this equation, once it's written in explicit form, we can find an expression for the invasion parameter. So we can understand which are the aspects that determine epidemic confinement or epidemic invasion. So I don't write here the explicit form because it's quite huge, but you can see that this function of the basic recollected number, of course, and all the other parameters that are related to mobility and demography. And then we have that function h, that is function of the topology of the network. So we can plot the invasion threshold parameter as a function of the parameter of the model. Here in particular I consider the basic recollected number and the exponent key that use the heterogeneity of the random state distribution. So when a star is greater than 1, we have the invasion. When it's below 1, the epidemic is confined. So we can see that, for instance, the basic recollected number play an important role, and this is quite expected. So larger is the basic recollected number, so more transmissible is the disease. Greater is a star, so we can go from a situation of confinement to a situation of invasion. But the interesting part is that also key play a crucial role. So here we are comparing situation with the same length of stay averaged all over the system, but just the distribution of the length of stay is different, and we can see that a star changed completely. So for instance, for an R0 1.2, that is a value that could be among the estimates for seasonal influenza, for instance, we are much above the invasion threshold with a positive value of key, and below the invasion threshold for a negative value of key. Basically, when we have a positive correlation between degree and length of stay, we are enhancing the spreading potential of the disease. And we can see this also by looking at this plot. Here we are looking at the spreading pattern of the epidemic, so we are above the threshold. So I'm showing you the invasion tree for two different value of key. So the node in the center of the picture is the origin of the epidemic, and then I have all the nodes connected to him, and the dimension of the node is proportional to its degree, and the color code indicates the time in which it's infected. So here, when we have key positive, basically I infected first the high degree nodes, and that they are important in further propagating the disease, while the low degree nodes are the last to be reached. And when key is negative is the opposite.
I mean, you change the exponent, but then what you keep constant, the coefficient is the same, or you normalize in a different way?
The coefficient, do you mean? Sorry.
Yeah, the tau is the same?
No, it's not the same because I want that I keep this quantity, I average it on the whole system, and I want that it is the same in my case.
So the average time is the same in all sequences, so you normalize in the...
I'm just playing with the geographical distribution of it.
And you don't have problems for exponents which are small, that the average does not converge and things like that?
No, I really have to be careful. I mean,
so it means which is the heterogeneity distribution of the k you are using? Is k? Is a power law with which exponent, or what is it?
K?
The probability of the degree.
It's power law.
Of
Which exponent?
Because this is another exponent which will enter into the...
Yeah, that's important. I think that, usually we test value between 2 and 3 because these are the values estimates from empirical network. In particular, for the spatial network, the estimates is 2, but in general, it was shown that is the limit of infinity will be scale free. So this is the kind of value that we use in this model. But actually, since I'm not interested in the infinite limit, I'm working with finite system, the particular value is not important. I mean, between 2 and 3, that is realistic, it's the same. Okay. So I can conclude this first part of the talk. So we can conclude that length state heterogeneity completely alter the epidemic diffusion, the invasion potential in epidemic. And so actually we need to account for these ingredient in models, but actually the problem is that we don't have good data, so it would be nice to have a large data set in order to make a statistical analysis, plug it in our model. Okay, and now I want to move to the second part. And so the impact of multi-strain dynamics on the spatial propagation of epidemics. I will start by discussing the problem. So the point is that for many pathogens, we have the coexistence of different strains. These strains, in some cases, have different traits, that means different transmissibility and different infectious period. And in many cases, they compete for host exploitation. And one of the biological mechanisms determining this competition is, for instance, cross-immunity. So when an individual gets the disease from one strain and he recovers, he acquires immunity not only to that strain, but also to the other circulating strain. Since this process of competition is important for the evolution of pathogens, it's important to understand which are the determinants of this competition. And of course, there are many aspects to take into account, in particular aspects related to the biology of the process, like biological, immunological aspects. But also there are population level factors that are maybe important, like demography, spatial structure, and mobility. In particular, spatial structure and mobility are suggested to play a role, so to affect the competition between different strains. And so this is our question. So which is the impact of mobility on multi-strain competition? Actually, I will introduce a very simple model for the competition of different strains that address this question. So the framework is the same, metapopulation approach, and basically I change the 3 ingredients with respect to before. I will start from the 3rd ingredient because that's the more important now, so the transmission model. I will consider 2 different strains that are characterized by an SIR-like dynamics, and they compete with a total cross-immunity, so an individual that recovers from a state is completely immune to the other, also to the other. And we will assume that these 2 strains have the same basic reproductive number but different infectious period. This means that the 2 epidemics, characteristic of the 2 strains, are characterized by the same impact on the population, meaning that the same number of individuals get the disease at the end of the epidemic, because this is just function of the basic reproductive number, but are characterized by different evolution time scale. Indeed, from SIR equations, we have that longer is the infection period, slower is the SIR dynamics. So we have a slow strain, that is the one with the longer infectious period, and a fast strain, that is the one with a short infection period. Okay, so let's introduce the other 2 ingredients. So we assume we choose the system, the most simple system. So basically, the mobility network is considered to have an homogeneous topology, also heterogeneous. So in the simulation, we compare the 2 cases: power law-like, power law distribution, and Poissonian distribution. But we were able to make analytical calculations so only for the homogeneous case. And we assume a Markovian dynamics, a simple Markovian traveling dynamics. And we assume that all individuals leave their location with a probability P. So this model is very simple. And moreover, as initial condition, we choose that the 2 strains originate from different locations. So at the beginning, they don't interact, but when they start to spread on the mobility network, they start to interact. So with this model, we first made simulation, don't need to see what I meant. So stochastic simulation of the spiral dynamics. And what we found is quite interesting. So basically, the competition between the 2 strains is determined, completely affected by the mobility regime. So here I'm showing you the fraction of infected patches by the 2 strains, the fast and the slow one, as a function of the travel probability. So we can see that for large value of P, so a lot of people travel and the system is well mixed, the fast strain dominates. Indeed, it creates almost all the patches, while the slow strain is confined in a small fraction of the system. And then, as soon as we decrease P, we have the situation change until we reach a crossover, a critical point in which the 2 strains coexist. Basically, they reach both of them after the system. And then the slow strain dominates, and at the end, of course, if the traveling probability is very, very low, or very, very low, nobody travels, and so none of the strain is able to spread. Okay, I'll show you other results, other numerical results. The first plot is the coexistence probability, that is the probability that the 2 strains are found in the same node, and is increasing. Here I'm comparing the homogeneous and heterogeneous network. In both cases, the is the coexistence probability is an increasing function of p, but in general is quite low. So the two strain doesn't coexist so much within the same patch. And the second aspect that I'll show you. So here I'm looking at the distribution of the two strain at the crossover regime. So P is equal to P in the crossover regime, and I'm looking at the fraction of infected cities within the degree block, the degree class K. So in this case, we saw that the system is divided into areas, one affected by the fast and the other affected by the slow strain. But they are distributed in a different way. So in the high degree nodes, the fast strain is dominant, while in the low degree nodes, the slow strain is dominant. Okay, so we can understand these passing results by trying to provide an analytical, simplified analytical model.
PC is a critical point, is a crossover, or how you characterize PC? Just where they cross, where the fraction are the same?
Numerically, you can see just where they cross. Basically,
so it's not a critical point?
Yeah, sorry.
No, just asking.
Yeah, crossover, yeah. Yeah. Crossover coexistence. OSC, basically. Okay. So, analytical understanding. So, basically we make a comparison, an analogy between the SIR dynamics at the level of individuals and the sort of SIR dynamics at the level of patches. So, at the level of individual, we have an infection duration that is mu to the -1, and then we have a basic reproductive number, and we can see that at the beginning of the epidemic, the number of infections grows exponentially with this expression. So if we make a comparison, it's quite rough actually, but okay, it's just a reasoning at the level of patches. So instead of infection duration, we have the outbreak duration, and instead of the basic reproductive number, we have R star, that is the inversion threshold parameter. So we can say we approximate the inversion dynamic among patches like this exponential growth that is analogous of the previous one. Okay, in the case of an homogeneous network with a simple homogeneous traveling probability P, R star have a simple expression like this that make us able to do calculation. And before that, we can look at this expression and we can already understand something. So basically, R star is an increasing function of the infectious period. So a star characteristic of the slow strain is greater than the one characteristic of the fast one. And but also its R star is obviously an increasing function of P, in the sense that more people travel, greater is the invasion potential of the epidemics. So basically we have two distinct situations. A situation in which P is very large, but R star for the slow and R star for the fast strain are much greater than 1. So the two epidemics are able to easily spread and percolate through the system. And in this case, the relevant aspect is that the propagation speed. So the fast strain is faster, so it reaches rapidly all the patches, and the slow strain is not able to spread anymore. But when we have a small value of P, the fact that the R star for the slow strain is greater of the R star for the fast strain become important. In this case, the slow strain is more able to percolate through the system, so it is able to overcome the fast one. So this explains this changing of behavior invariantly. And within this very simple analytical framework, can also find an estimate of the crossover traveling probability. And this is quite simple. So basically, we neglect an interaction among the two strains, and we consider the point in which the ratio among the number of effectivity by the slow and the fast strain is equal to 1. So this means solving this equation. So the two exponential growth are the same. And with this very rude analytical model, we can find estimates for the crossover probability. It is match pretty well the numerical results. So we are quite happy. Here I'm showing the crossover probability as a function of the basic exponential number. And so I have concluded also this second part. So the take-home message is that we found that how spatial structure and mobility actually determine the outcome of pathogen competition, multi-strain competition. And yes, we were able to provide all numerical results and analytical understanding. To do next on this is to go toward virus evolution. So we want to model also virus mutation and so the generation of new strains and see how they get extinct, which is really the evolution. Okay, these are my collaborators. So this is a reference of the first part of the work. So Michele Tizzoni worked with me on the length of stay and Vittorio Colizza, while the second part that is not yet published is in collaboration with Vittorio Colizza, Sandro Melloni, Emil Moreno of BIFI, and Sandro Visconti.
Okay, so let's see if there are more questions.
So what is telling you this last part for the competition of flu strengths between different years? Because the mobility probably is very similar one year and the next, right? So the P is the same. So can you
flu?
Yeah, flu because you have different strengths, but probably you can. You can also.
Detail on flu, I don't know. Actually, I don't know. I mean, the point is that here is really the evolution of the virus. So the problem is how virus evolve to adapt to humans. And this is a general question that is important, for different pathogens. For the specific case of influenza, I don't know, but in general this is the problem. And
but for the flu, essentially what we have is they are like there are many types. A number is the different strengths. There are sorts of combinations, but typically what you have around is the influenza B, which is one type, and then there is like two of the other, H something around every year. No? And the most common one changed, so there is a shift every few years. But there is something to take into account, is that these strains are mutating all the time. So the parameters of the infections of this mu and beta, which is the one that gives the zero, are also changing. So I don't know how these things really happen. There is this competition.
So, no, of course this is related to influenza, but in that case it's not like the evolution of the traits, so evolution of infectious period or transmissibility. It's not that the most important part for the case of influenza. For the case of influenza is to predict the evolution of the virus in order to be able to make vaccine. So because virus continuously evolve.
Yeah, okay, so then what is an example for more realistic for this approach?
There are many examples of adaptation of the virus to host. there are many stories about that. So basically, virus that after a while become less virulent because otherwise they kill completely all the host, for instance. And there are different stories about this regarding pathogen that is introduced in the population to kill animals because there is too much rabbits, for instance, and but after a while the pathogen adapted to the host and doesn't kill the rabbits anymore.
No, I mean this model is a good approximation for the flu, but for a short period of time. You cannot consider it in many years because then the pathogen mutates and all the parameters change. But maybe in a year for the different strains.
No, I mean,
you wanted an example, no?
Yeah, I mean, trying to see whether the mobility, as the mobility I expect from year to year not to change much, and here you have some prediction.
So now
the pattern should be similar.
The question is, which is the pathogen that is advantage in the system. So here the answer is depends on the mobility value in this case. So
we have a nice analytical argument that gives the data, but I don't really have an intuition on it. But I have another very simple argument, and I don't know if it also fits it. I would say that the fast strain will so there will be a transition between dominance of the fast and the slow when the time for jumping between different patches is slower or smaller or larger than the outbreak time. I think this will, so the critical inverse of the critical peak will be the time of the outbreak. Is this idea consistent with the data?
That's the point. I mean, if the outbreak is too short, if you have a small flux of people traveling, there is not enough time to send an infection individual in the new patch. So the fast strain is not able to propagate. But the slow one has more time. So basically, we are introducing a time scale, it is the traveling time scale, that is a discriminant among the two, and choose basically between the two.
So I have a question on the first part. They will introduce the heterogeneity on the length of stay. This length of stay depended on the degree of the place you're coming from or the place you are traveling to.
You are traveling to.
So we assume that people who travel to London stay very much, and people who travel to Mallorca stay very little, or something like that.
Yeah, depends on which. Yeah, exactly. So depends on the destination, and then in varying key, I'm varying different scenarios. So if key is positive, you spend more time in London, because I guess that London has more connection than I don't know, but. So you spend more time in London. If key is negative, it's the opposite. You spend more time in Mallorca.
So this effect we observe is because the length of stay is coupled to the degree of the place.
Yeah.
Do you have any justification for this? And do you have any data?
This is the biggest assumption in the model. We don't have a good data set to do. I guess that there is a correlation actually. But the problem is that, I mean, the data set that I show you, the random UK is the only one that we found. And with that, we cannot cover any relation with the degree.
So let's say not so much heterogeneity in the length of stay, but the coupling with the one that has a peak.
Yeah.
But my intuition goes in the opposite direction. When you go to a place which is very well connected, you are able to just go there, do whatever you want to do, and leave. While when you go to an isolated place, many times you have to remain there for a few days.
Yeah.
Well, it's the opposite. When you go to a big place, you have many things to see. When you go to a small place, you just move to another and another.
Well, when you go on vacation, you go to an isolated place and stay there all.
Well, true, but this is not enough. Come to Magaluf.
Yeah, about the reasoning are good. I don't know.
Because degree final is connected to population, right? So big degree means big places.
You mean in connections?
No, I mean connections is an abstraction because final is related to a track. So the more people, you expect to have more connections.
But that's not proportional.
That's not proportional.
Papa Mallorca has more connections proportional to population than you.
Sometimes I forget. I mean, we are talking about averages, not
Yeah.
spatial points that you always find.
Well,
I mean, when you take Mallorca, you can remove it. The measure of Mallorca is C. So you cannot take Mallorca as an example for these things. So you have to compare places with the same population like Mallorca, and then you are going to see that the airports are not so big.
No, but come on, when you travel through Europe, if you go to London or Paris or Zurich or Frankfurt, and you have to do something, you can go there and come the same day or the day after. If you have to go to Helsinki, it will take you 3 days to go and come back.
Yeah, right.
Well, from here, but not from Germany, the population is larger in Germany. But I mean, you spend more time, I don't know, I mean, just think when you go on holidays, you go to New York, or if you go to, I don't know.
To Maldives.
But it's a matter of time in a place or a matter of geographically you're being affected. I mean, in a place which is slightly connected.
In Mallorca for a while, I don't know if this is still done, but for a while the UID was conducting statistics on the people living in Mallorca, asking how many days they have been here, and so many things. And this has been done several years on the road. And there should be statistics, for example, of the people here, from where they come from where they can go, I mean, how far away they have traveled, how many days have we spent here.
Yeah,
The statistics are there.
But I can tell you,
I don't know what I
here
mean,
basically the hotels they run for a week. And they
Yeah,
have-
but they were, these statistics,
So
they
this is
were asking
typical.
to people, I mean, they were asking this to the
Well, you
people.
go to a hotel and you see when the buses leave.
Yeah,
And you see that on Saturdays you have more buses, and most of the people go from Saturday to Saturday to Sunday to Sunday. That's what most of the people do.
that was statistics counting everybody. I mean, the ones that come with an organized tour, the ones that come with.
But I don't know if this is representative for Paris, for example. If in
No.
Paris you have the same restrictions.
Maybe the same statistics that were done here were done in other places.
For me, basic assumption is not.
It would be interesting because if there is, maybe there is a correlation with it, I don't know. But if there is a correlation with the degree, this was a slide, I mean, the picture completely changed. So basically, since we have that the network is extremely heterogeneous, what we find is that a correlation, positive correlation with the degree enhances the heterogeneity of the system. So the system is much more heterogeneous and it further favors the epidemic spread. Otherwise, if we have an anti-correlation with the degree, we compensate basically the topological heterogeneity because we spend less time in a well-connected city. Okay, so the role of the well-connected city is reduced. And so the picture, because the usual picture in the spreading of the diseases on the heterogeneous network is that nodes with a large number of connections are crucial for the spreading of the disease. And but if the time spent there is less than the other, they become less crucial. So basically, we are completely compensating this. So it would be interesting to understand.
I mean, I don't know if this is significant or not, but it is clear that when you organize a scientific meeting, if it is a one-day meeting, it is in a very well-connected city.
Yeah.
If it is a week meeting, it is in an isolated place.
Yeah, but do you have to normalize with the people that go to conferences?
Yeah, well,
I'm just saying that. I mean, that's.
I don't know.
If you go to London, you go for a day.
If you are business partner, go.
And did you have data on when to stay public because
So,
I'm really
but
curious.
essentially, I mean, to me, I mean, the most important thing is somehow that the time scale of the infection has to resonate with the state. So if the time scale for the infection is a week, then this infection will resonate with people staying there for a week.
Yeah,
So if the states are shorter, then the thing will die. So I think this is the key.
This is very important. Actually, I didn't discuss about this, but this is important.
And perhaps you can compare different infection rates with respect to where they are more prevalent.
Well, yeah. No, okay. The interplay between the two time scales is very important. But in particular, this kind of all this picture is important for long diseases. If diseases are fast, length to stay is not so important. I don't know if I explained it. We can discuss later about this if you are interested, but no, it's fine.
Well, yeah, if, that's something that I was going to say. She's going to stay today up in my office. So if anyone wants to talk to her, let's go through them. Okay? So and then let's thank her again. And,
So 3, 4, 5.